The next step to understand the effect of dopants is to look at the band diagram of a doped silicon. Here, we draw the band diagram across a few silicon atoms with a phosphorus dopant. At the location of the phosphorus atom, there is one extra outermost electron associated with it. At the same time, a phosphorus core has one extra positive charge compared with a silicon atom. Therefore, there is a stronger attraction to electrons, and electrons can stay closer to that atom core or the valence band. More macroscopically speaking, over the entire solid, some electrons can stay at an energy in the band gap where they are not allowed to stay in intrinsic silicon. We can also say that the donor dopants introduce a donor energy level, denoted by ED, at which electrons are allowed to stay. Similarly, by adding a boron atom to replace a silicon atom, it introduces a loosely bounded host. As a result, electrons in the valence band near the boron can stay a bit further away from the nucleus at the acceptor energy level EA. It is the same as the case with donor dopants, except that it happens to the valence band and hosts are considered. If we zoom out the energy bands over a larger area of phosphorus-doped silicon, you can see that there are many small dips in the conduction band at each location with a dopant. Considering the density of silicon atoms is in the order of 10 to the power 22 per cm cube, the density of dopants is usually in the range of 10 to the power 15 to 10 to the power 20 per cm cube. It is due to the solid solubility limit in the amount of dopants silicon can take. In addition, if too many dopants are added, the intrinsic properties of silicon may not be preserved. Given the low dopant density with less than 1% of silicon atoms replaced, the locations of the donor sites are very sparse. As the energy difference between the donor level and the average conduction band energy is very small, the electrons inside the dips in the conduction band can easily come out of it and move around the conduction band as long as some energy is given to it. Once an electron comes out of the dip, it may not be distinguished as coming from a dip, and it just moves around over the entire conduction band. Therefore, we can assume all electrons coming from the donor dopants will be delocalized and become electrons in the conduction band. Even when these electrons fall back into the dips, they will come out again easily. In N-type silicon, the electrons significantly outnumber the holes due to the donor dopants. We call electrons in N-type silicon the majority carriers, and holes are referred to as the minority carriers. The situation for a P-type semiconductor is similar. An acceptor dopant creates a state unoccupied by an electron, which is a hole, near the edge of the valence band. It can be easily filled by an electron, and the hole is pushed down to move around in the valence band. In a P-type semiconductor, holes in the valence band become the majority carriers, while electrons in the conduction band become the minority carriers.